structure and bonding. I think structure and bonding is the most important topic personally, perhaps after atomic structure. You are guaranteed to get questions on this in paper 1. You're always going to get some substance that you have to describe the properties of or explain the properties of by referring to its structure. So you have to be confident when you see on a question paper, what kind of substance is this? And that's what you've got to get your head around to start with. I'm not going to do, in class I've done this, and I've actually made a load of videos breaking down each of the substance types which you can go back to and have a look at. But in this session here, we're going to go straight to the exam questions after a very brief introduction, which is around the different types, the 4 different types of substances. But no detail here and now, we'll do that on the paper. So you've got to basically decide before you start explaining what sort of substance it is, whether it's giant or simple, and it's easy to do. So if it's just a metal, it's giant, and it'll be giant metallic, and that's just any metal, right? And we'll go through what that looks like and what the properties are and the structure are and all that kind of stuff in a bit. And so any metal, zinc, copper, iron, whatever it is, would have similar properties to each other and similar structure. A metal and the non-metal would be giant ionic. So metal and non-metal. I remind you yet again that metals have got a plus in the middle of the word, which is how we know metals always form positive ions when making compounds. And non-metals have got a minus in the middle of the word, which is how we know non-metals always form minus ions when they form compounds. Just remind you, of course, that metals are anything in that part of the periodic table, anything to the left of that zigzaggy line that I've put there. Or you've got giant covalent. And there's just a number of substances you have to know about that are giant covalent. So diamond, graphite, silica, which is exactly the same as diamond really. Silica and diamond, graphite, or a single layer of graphite, which would be graphene, which has got some interesting properties. And each of those you have to learn in turn and know in turn what they're all like and they're all about. It might be though that you've got a small group of non-metal atoms attached together, so anything with just nitrogen, carbon, oxygen, hydrogen, maybe sulfur, maybe chlorine and fluorine, any of those non-metals joined together in some way, whether it might be CH4 or O2 or N2 or H2O, any of those things, a small group of non-metal atoms, could be the same atom like in H2, or it could be a whole group of different atoms, and maybe a molecule you've never seen before, like that one there, a small group of non-metal atoms joined together. That will always be simple, and it will always be simple covalent. And you've got to be able to draw and describe and then explain the properties of these substances. So working out what it is first, and then away we go. But I'm not going to go through each of those in turn. Watch the videos for that. Tried to make sort of 8-minute videos on each one of those things. They're not quite finished yet, but I'm part way there with it, which you can find dead easily. But what we're going to do is going to just burn through an hour's worth of questions here now, or whatever we get round to. So we're going to start off with this one here. I'm going to talk to you about how we draw these dot cross diagrams. I did it yet again with my class today, and yet again many of them didn't do things the way that I've taught them. So I'm going to remind you again, if you're asked to draw a substance, the first thing you do is work out what substance type it is. This molecule here, the word molecule refers to simple covalent, by the way, it's a small group of non-metal atoms, so it must be simple covalent. So this is just for yourself really, and I'll speed up as we go. But if it's simple covalent, we know we've got to the definition of simple covalent, which is shared pairs of electrons. Again, don't want to spend too long on the detail here, but that could be worth a couple of marks in a different question. But here we've just got to draw the dot and cross diagram. The way to approach the dot and cross diagrams is always exactly the same. you should know how many bonds each of the atoms make based on their position in the periodic table. So you look at how many spaces there are in the outer shell of that atom. So if it's hydrogen, there's 1 space. If it's oxygen, there's 2 spaces. Carbon, there's 4 spaces. Chlorine, there's 1 space. Nitrogen, there's 3 spaces, in the outer shell. We can know that from the periodic table. So we know how many bonds they make, because when you make a covalent bond, they've got to get those electrons and fill the outer shell with them shared from another atom. So the way to start doing this is go, well, I've got a hydrogen and a chlorine. Hydrogen and chlorine both make 1 bond, so we draw the line diagram. Line diagram just shows the bond. It shows the bond which represents the pair of electrons. This is a very simple question, obviously, just a 1 bond, 1 line, and so we get 1 mark for then drawing it as they want us to, as a dot cross diagram, showing that line, which is a shared pair of electrons represented by either 2 dots, 2 crosses, or ideally a dot and a cross. GCSE don't care whether you draw dots or crosses and which way round, or whether you get them, as long as you've got 2 electrons in there. Make them big, make them easy for the examiner to see. They come through on the screen of the examiners as a kind of blur if you're not careful, so not just full stops but big fat dots. But that would get you 1 of the 2 marks. You must remember that when we make these diagrams, all of the atoms have got to have full outer shells, and all of these atoms can have 8 electrons in the outer shell. All of them, with 1 exception that you need to know about, have 8 in the outer shell. The exception is hydrogen, which can only get 2. It's a very small atom, it's a very small outer shell. So to finish this off, all we've got to do is to make sure the chlorine has got 8 in total in the outer shell. There's 2 there, so we need 6 more. And chemists like to draw them in pairs for reasons we talk about in year 12. We won't worry about that now. And so that's going to get you 2 marks. Right, that's the approach we'll take, and we'll hopefully see another couple of examples of that. But before we do, I'm going to show you another. There's going to be a few on simple covalent. So again, non-metal atoms in a group. Let's start by drawing and turning this into a dot cross diagram. You have a go. I'll do it here. You can check your answer in a second. So draw your own version of it. So methane CH4, draw it as a dot cross diagram, compare it to mine. CH4, yeah. Remember that each carbon makes 4 bonds, each hydrogen makes 1 bond. And that's what you were told in the question. That's what I've been calling the line diagram, with each pair of electrons represented by a line. So to draw it as a dot cross diagram, we draw it with each line represented as a dot and a cross. And then we make sure all the atoms have full outer shells. And what you should end up with, and I'm looking around, I can see quite a few of you are nearly done. So just check your answer with mine. It should look something like that. Right. But it asks you here about the melting point of methane, along with another substance, the polymer next to it, and we'll talk about that in a moment. But you should know this applies to every single simple covalent substance. So every time there's a small group of non-metal atoms joined together, they always have low boiling points. That's another little point to make, and again, you'd have covered this in class lots of times. But why do they exist in different states at room temperature? So I would simply say here, methane has low boiling point. And forgive me for writing shorthand to make things efficient here, but low boiling point. In an exam you write fully low boiling point, which is why it's a gas at room temperature. And you'd say the explanation for that is the same every time, whether it's nitrogen, oxygen, H2, Cl2, anything. It's because there are weak forces between molecules, or if you're feeling clever you can write weak intermolecular forces. Molecular forces between molecules which require little energy to break, or not much energy to break. hardly any energy required to break those interactions between the molecules. Now, it's worth drawing that. I'll try and draw it if I've got a bit of space here, just to represent what's going on there. Some of you won't be very confident at this, but if I draw, rather than draw the line diagram like in the question there, I want you to think of simple covalent substances as little clusters of atoms joined together. When you boil them, you absolutely do not break the strong covalent bonds. Ionic bonds are strong, covalent bonds are strong, metallic bonds are strong. You can't break them by simply boiling them. Instead, what you overcome are these weak forces that form between molecules. You don't have to learn at GCSE how they form or why they form. All you need to know is that the bigger the molecule, the bigger they are, even though they're still tiny in strength compared to covalent bonds. So these are called intermolecular forces, and they require little energy to break. Common as anything, that question. Nearly every, probably most years, I would say. Polyethene is a polymer, and we're not going to spend much time on polymers today. You can imagine, or remember hopefully, that polyethene is a long chain of carbon atoms, long chain of ethene molecules that are chemically bonded together, and they end up kind of a bit like spaghetti in a pot. And there are still weak forces between those polyethene chains of molecules. But because those polyethene chains are so long, they're literally hundreds and hundreds of atoms long, the intermolecular forces are just that bit stronger, and so the melting point goes above room temperature. I think that's quite a difficult question. So I would say in words, if you want to write something down, you've got something about long chains of carbons, stronger intermolecular forces, require more energy to break. This is just a comparison question. And that principle applies to lots of examples. So down group 7, F2, Cl2, Br2, I2, the boiling points increase because the molecules get bigger. Crude oil and fuels, as you go from methane to ethane to propane to butane to the longer chain ones like petrol and diesel and fuel oil and bitumen that you've learnt about. The longer the chain, the stronger the intermolecular forces between those longer molecules, more energy required to break them. They're still simple covalent. They're still nothing like as strong as the melting points of any of the giant substances, metals or ionic or covalent substances. Let's move on. I feel like I wanted to say something else that I've forgotten. Yeah, the only little thing I was going to add to this is if you get a question about, what's it called? Thermosetting polymers, they are linked with strong covalent bonds. Remember, those cross links, and you can't melt those and reform them. So that's a little extra detail I thought I'd add. Right. You might remember you studied, probably for about a quarter of one lesson last year, you might remember you studied some strange molecules and substances that are also made of carbon, other allotropes of carbon. So this particular one you won't have seen before probably in the lesson, the C70 rather than C60. It's still a sphere, it's still a ball with carbon in rings with 6 or 5 membered rings around the ball. But this particular one is C70. You've heard of C60. There's loads of them actually. And the name of that type of molecule are fullerenes, and they are, again, simple covalent, by the way. Even though they remind you a lot of graphite and graphene, the way that it's bonded, they're actually simple covalent. And the reason they can move drugs around the body, it's worth remembering, is because they're hollow. Right? Hollow there. This is a question which comes up every couple of years. Yeah. Because they can roll over each other, they can be used as lubricant. And that question was in the year 10 test on this topic that we did. Yeah, they roll over each other because they're spherical. Yeah, like marbles, I suppose. Good. And there's another one, another different year. Same thing, fullerenes, balls of carbon atoms. What shape is it? It's spherical. So another question about that. Oops. Spherical. And a use of a fullerene, lubricant, Taylor's just said it there, or carrying drugs around the body. But the reason I've really got this page here is because I want to practice drawing this, or looking at this dot cross diagram here. I don't like this picture very much, and the reason I wanted to show it to you is because I don't like it. If you did this in an exam, the examiner might be a bit sniffy about it, because normally we talk about covalent bonds as being shared pairs of electrons between the atoms, and I'd much prefer it, personally, if those pair of electrons were inside the overlapping region. What's going on with this bond here? I thought I'd ask that. What's going on with that one? I've just put a ring around. What's going on there? There's 4 electrons in there, so what type of bond is that? Shout it out. Yes, it's just a double bond, right? Good. Right, so then it wants you to represent that as a line diagram, and what was it, propanone? And so if we represent that as a line diagram, would end up with this. Can you see how you can flip from a line diagram to a dot and cross diagram? It's the same thing, just shown in a different way. So the reason I picked out that question to show you, to represent the fact that you can draw molecules in different ways. They're only models, we can't really imagine what they'd look like. They're much smaller than we could possibly imagine, but you can draw it in both those ways. So you might have to convert from one to the other. So just be careful as well. I think it was the mock exam, it was certainly an exam you or some other group did recently. Lots of questions were missed out like that, where you had to fill in diagrams. Just look down the side, make sure you're checking off every mark, make sure you've answered every question. But sometimes you get these sorts of pictures, sometimes you get space-filled pictures, and they say, well, what's the formula? When it says what's the formula, it just wants you to tell, they just want you to tell them how many carbons there are. There's obviously 3. How many hydrogens there are? 6. And how many oxygens there are, which is 1. Okay, easy peasy, but it's amazing how often people really struggle with that, particularly when it's photographs of the kind of models we use, those, what do you call those, mods in the classroom. Right, you're all going to just tell me the answer to question 1.5 on a countdown from 3, because we've just talked about it. 3, 2, 1. Yep, you're all saying the bottom one. Good, well done. Again, one more repeat, then we move on to a different bonding type. So you notice I've just done simple covalent over and over and over again, but it's time to move on shortly. So the halogens, group 7, F2, Cl2, Br2, I2. Tell each other now, please. For 4 marks. What are you going to get 4 marks for? For explaining the boiling point of those substances, F2, Cl2, Br2, I2. What's the trend? Why the trend? Remembering, of course, that they're just non-metal atoms. Discuss. Very, very common question. Questions like this, which talk about these intermolecular forces. So, first mark will be something like, and you can just shout yes if you got the mark. You've got an increase in boiling point down the group. You actually say what the data is. Yep. Shout yes if you got it. You would say that the intermolecular forces increase down the group. Yes or no? Yeah. They get stronger, or the strength of the intermolecular forces increase, or they get strong. Oh dear. Strength of intermolecular forces, or the intermolecular forces get stronger down the group. The next thing would be because simply bigger the molecule, the stronger the intermolecular forces. So because you've got increased molecule size, or you could say ideally you'd say you'd have a slightly higher level answer, more electrons in each molecule. As you get bigger, they get more electrons, and those number of electrons links to the number of, or the strength rather, of the intermolecular forces. Who got that one? Yes or no? Yeah, good. And the last one would be so more energy required to overcome these these intermolecular forces. Right, that's it. Who got that last mark? Yeah, good, well done. Anything, think I've missed anything? Good. Right, skip that. Another dot cross diagram. Can you all do that dot cross diagram, please? And just verbally discuss 5.3. So the dot cross diagram, everyone, then 5.3, then we move on to different stuff. Because you like? Good. Most of you got it right. Each line would have represented a pair of electrons. Make sure those electrons, look how bad that is, look how badly that would scan for an examiner. If it's that bad, draw it again, right? I've only got 6 in the outer shell of nitrogen at the moment, so I need 2 more, and I put them up there. Job done, 2 marks. You get 1 mark for those 3, 1 mark for the 2 at the top there. 5.3, though, is around ammonia having a low boiling point. And I heard the answer correctly lots of times around the room, because we've just done it. Most of you can do it in a couple of weeks. Low boiling point because of weak intermolecular forces. So weak intermolecular forces they require little energy to overcome, or little energy to break. We don't break the bonds. Another one there, we'll skip that one. These are all going to be scanned and shared with you, all of these questions. So there's more of the same here. Right. Next thing we're going to move on to then is... Where's the back? Next thing we're going to move on to is ionic bonding, though. So I never want you to talk about just ionic bonding. You talk about giant ionic, giant metallic, giant covalent if it's diamond or graphite or something, and simple covalent. So don't just talk about ionic on its own. Make it clear what it is. This is a compound made of potassium and sulfur, and just like all bonding types, we're going to end up with full outer shells for reasons that we're going to just ignore for now. So how would you show that? Now it says here to describe what happens when potassium and sulfur react together. It's a good opportunity for us to practice how we draw this. And I know again from teaching classes this week how hard people find this to get exactly right. First thing is to recognise that you've got a metal and a non-metal, and so we should be spotting immediately that it's ionic. So do that first, and then you can lean back on the knowledge that you've got. Potassium's a metal, so it's going to form a positive ion. Sulfur's a non-metal, and you're going to end up with full outer shells. Potassium's got 1 in its outer shell, so it's going to end up with a full outer shell by losing that electron. Sulfur's going to form a full outer shell by gaining that electron. But there's an issue here, isn't there? Sulfur's got 6 electrons in its outer shell. Potassium can only give it 1 electron. So there must be a second potassium. Which is why we represent this. I'd probably represent this as a picture, even if I had this as an exam paper. Show those 2 electrons moving from each of the 2 potassium atoms to make 2 potassium ions. So to describe what happens, say 2 times K atoms lose, I don't really want to write it all out, lose 1 electron each to form a potassium plus, or to form potassium 1 plus ions. 2 times potassium 1 plus ions. We would show that, if we were to draw it, the potassium with a plus, so we'd show that potassium ion like that, and ideally show that there's 2 of them. But then we'd say sulfur gains 2 electrons to form sulfur 2 minus ion, and we'd show that like this. So we've got a sulfur 2 minus ion. Again, we show those ions with square brackets like so. So we end up with potassium sulfide, 2 potassiums and 1 sulfur. It doesn't ask us in here at all about the properties of ionic compounds. Be careful to read the question. What's it talking about? So we've got to talk about the transfer of electrons from potassium to sulfur. So let's get that word in our answer as well. So transfer of electrons. And it's worth pointing out, I think, as well, if you take a metal and a non-metal and react them together, we can link this a little bit to the redox topic. Potassium has gone from potassium with however many electrons it is, I can't remember, and it's lost one. So if it's lost an electron, it's been oxidized. The sulfur has gained an electron, so it's gained 2 electrons, so it's been reduced. Remember, that kind of links to the redox topic, which you won't have done when you first did this. Oh look, funnily enough, that's the next question. So oxygen is being reduced in a different equation, and sodium is being oxidized, and you just talk about the fact that when ionic bonds form, make a note of this maybe, when ionic bonds form, the metals are oxidized, the non-metals are reduced. And that's always true. The non-metals gain electrons, the metals lose electrons. And don't forget sort of oil rig. Oxidation is loss of electrons, reduction is gain. So for a question like that, you'd say electrons are gained. Okay? But what's more important, so metals are oxidized always because electrons are lost. Non-metals are always reduced because electrons are gained. But the much more common question, this is quite an unusual question I would say, but the next question is a very, very common question, and you're very likely to get a question. It's probably every other year you'll either get, or possibly both, something about the low boiling points of simple covalent substances like we were just doing, or it'll be a question about the high melting point of metals, ionic compounds, giant ionic compounds. What often happens now is that people muddle those two things up and go, oh, it must have strong intermolecular forces. But that's not right, because the word intermolecular forces refers to those weak forces between those small groups of atoms we were just talking about earlier. With ionic compounds, we need to remember that these form these three-dimensional lattice structures. And again, I mean, here's an example of one in a different picture here. Quite a complex lattice, this one. You wouldn't have seen a lattice as complex as that before. But you can see that you've got these three-dimensional structures with strong ionic bonds between the ions. Those require lots of energy to break. And that's your standard answer used again and again and again. It could be sodium oxide, lithium fluoride, potassium chloride, magnesium oxide. It doesn't matter. They always have a relatively high, much higher melting point than any simple covalent substance, because you've got lots of strong ionic bonds between oppositely charged ions which require, and it's often this mark is lost at the end, which require lots of energy to break. So question for you, if you mention intermolecular forces now, do you think they'll ignore it or knock a mark off? What do you reckon? They'll knock a mark off, right? So if you mention intermolecular forces when we're talking about ionic substances, or talking about metallic substances, or talking about giant covalent substances, they will knock a mark off because of evidence of complete lack of understanding that intermolecular forces are related only to simple covalent. It might feel like I'm labouring a point, but I've seen it wrong so many times that it's worth pushing, I think. So this is your absolute bank of sort of flashcard question, I would say. Right, so a chance for you to have a go at a very similar question to the one we did a minute ago. Sodium reacts with oxygen to produce a giant ionic substance, sodium oxide. Oxygen's in group 6, sodium is in group 1. So when you're doing these, first of all draw the sodium atom or atoms. First of all draw the sodium atom or atoms and the oxygen atom or atoms, and then show the transfer of electrons, then show the ions that produced after that. So go ahead and do that, please. Let's go. Right, when you're drawing ionic compounds, as we did with the one before, we must start by drawing the atoms. So we often will draw the whole atom, but for the purposes of today, we're just going to draw the outer shell. So there's the sodium atom with 1 in its outer shell, and here's oxygen with 6 in its outer shell. I'll draw those as crosses. Sodium's got 1 in its outer shell and oxygen has got 6. Sodium can only give away 1, but oxygen needs 2. So we must have 2 of these. And you're going to get credit for recognising that you need 2 atoms here. So you start by drawing the atoms to show that we understand what's going on. As we said before, the metal atoms, the sodium in this case, will be oxidised. Will lose an electron to form sodium 1 plus ions, and the oxygen will be reduced. It will gain 2 electrons to become an oxide 2 minus ion. And so we can draw that underneath. Now please don't turn these atoms into ions. It will look like a mess if you try and do it all in one picture. So you start with the atoms and then you draw the ions. I should have drawn the outer shell here. There we go. So that's what it would look like, and that's what you'd put on your exam. So we're showing the atoms, showing the transfer of electrons, and then drawing the product like so. And remember, this would be a lattice structure of oppositely charged ions, and would have high melting point, but it doesn't ask anything about that, the properties at all, at least in this particular part of the question. All right, so pretty standard stuff. I tell you though that these are often done badly, so it's worth practicing them. Here's another one where you're going to do this verbally, just talk to each other. What 4 things are you going to say to tackle this question? Magnesium is in group 2, oxygen's in group 6 as well. So what are you going to say to get marks there? Just verbally, 4 marks. Have a chat. If you said that magnesium loses 2 electrons, yes. Or you might have said oxidized, if you're feeling really flash. If you said that the magnesium transfer those to the oxygen, yes? That word transfer is important here. Oxygen gains 2 electrons. And then, did you say that magnesium forms a 2 plus ion? Oxygen forms a 2 minus ion. You're getting the marks in. The last thing to finish this off, to bring it together, is to say that there's an attraction between, and I haven't talked about this yet, there's an attraction between the oppositely charged ions, which is why we get that lattice structure and those strong bonds which require lots of energy to break. Very quickly, question 6.1, a little bit about electrolysis. We've got a solid ionic compound. For electrolysis to take place, as you might remember from the redox topic, ionic compounds have got to be able to conduct, they've got to be a liquid. Why won't the ionic compound conduct when it's solid? This is a really common question. We've done lots in class, I'm sure. But ionic compounds conduct when solid, don't conduct when liquid. Discuss why now. Yeah, well done. I heard lots of good answers there. You say the ionic compound can't conduct, to be 1 mark, because the ions can't flow there. Fixed in a lattice structure is even better. Okay. But moving on now to giant covalent. Giant covalent. You've got to be sure that when you go into that exam in a couple of weeks' time, whatever it is, you know about graphite and diamond and silica and graphene and all of those. So we're going to go through a graphite question. Graphite, by the way, it's got a high melting point which you should be able to discuss, like any giant substance. But it also conducts electricity. Do you know why? Discuss. Right, so you have to remember the carbon's in group 4 to answer this question well. Carbon's in group 4, and each carbon is bonded to 3 other carbons. And if carbon is bonded to 3 other carbons, it's using 3 electrons to make those bonds. So each carbon is left with 1 electron. It's got 1 electron per carbon spare, if you like. Now that electron, did I say electrons? Got 4 electrons in the outer shell, 3 electrons are used in bonding to bond to 3 other carbons. Got 1 electron spare per carbon, and that electron is delocalized. Delocalized just means not localized, not fixed in place. It means it can move, it means it can flow. It can move around and carry that charge through the structure. So graphite conducts electricity. This is going to be more than we might need for these 3 marks, but we're going to get a bit of detail in here. So each carbon makes 3 bonds. Each carbon, and has 4 electrons. Each carbon, therefore, has 1 spare electron. That electron, or those electrons, are delocalized, and that's the key thing. So delocalized, not fixed in one place. Those delocalized electrons can flow and carry charge through the structure. And that answer is so similar, isn't it, to the answer you'd give for why metals conduct electricity. You talk about metals having delocalized electrons, you talk about metals having electrons that can flow through the structure, not throughout, but through the structure, carrying the charge. You need to say those things to get the marks when talking about electrical conductivity. Flow through the structure, carrying charge, right? So delocalized electrons carrying charge through the structure is where probably the marks are for. Should have checked. This is exactly the same. I'm not going to go through it. So if you see a nanotube, you see graphene, you see graphite, same answer. All graphene is a single layer of graphite, so the same arguments apply. All nanotubes are, if you think of them as rolled up graphene, same arguments apply. Each carbon making 3 bonds, and so on and so on. I don't want to do this question fully. This is a 6 mark. Look how common it is to talk about graphite. I put this back together to show you how common the questions are. We're not going to talk about graphite being a good conductor, we've just done that. I want to talk about why it's soft and slippery and why it's got a high melting point, like any other giant covalent substance. So, I'm going to give you a chance to discuss for just 30 seconds, and then I'm going to go through those 2 things. So the thing to remember here, as you were saying, as I was listening into your answers, was for any giant substance, whether it's giant ionic, giant covalent, as this is, and you would say that in your answer, or giant metallic, they all have high melting points. And that's different, isn't it, to the ones we talked about at the start of the session on simple covalent. Giant covalent substances have strong bonds between either giant, or these ones in this case, is strong covalent bonds between atoms. For ionic, it would be strong bonds between ions. Metallic, strong bonds between atoms, if you like, as well. Anyway, so here, strong covalent bonds between or lots of strong covalent bonds between carbon atoms require lots of energy, energy to overcome or to break. You have to melt it, you have to break those strong bonds. But graphite is an unusual substance, and it's very soft and slippery. And you can use it, by the way, if you didn't know, as a lubricant. I think I'm right in saying they use graphite as a lubricant quite a lot in space, because oils in space would be much more likely to evaporate, whereas graphite doesn't evaporate very easily, so it's quite often used where a lubricant is needed on the outside of spacecraft, things like that might need to move around. But we need to know why it's soft and slippery, and that's because it's got a layered structure. And if you're talking about graphite, and you're not getting in there somewhere that it's a layered structure, you're losing an opportunity. And those layers have actually quite weak forces between them that I'm drawing. You can't see that. I'm drawing sort of weak forces between them. And I like to think of graphite as just like a pack of cards. You know those big Sports Direct packs of cards? I like to think of it as those. So if you have one of those and you held them like firm, you can't bend or break them too much with really, but you can just break them apart by just sliding off the top one really easily. So graphite is soft, just like a pack of cards would layer by layer would slide off, and that's how they make graphene, right? They get some graphite, get some sellotape, and off comes graphene. It's that easy to break them apart. So layered structure, weak forces, or just really there's weak forces between the layers, but the thing you need to say here is that layers slide over each other easily. And I should check the mark scheme here, and I haven't, but layered structure, weak forces between layers, you could probably add there, and those layers slide over each other easily, which is why it's soft and therefore used as a lubricant. Guess what? It's more of the same. We've got time to do diamond as well. Now, diamond again is giant covalence, exactly the same arguments again and again and again. So let's deal with this one to start with, just verbally. It'll be the same answer you've heard me say already. So discuss that question, and then we'll come back to the next one, another one. Perfect. So good. So lots of strong covalent bonds between carbon atoms requires lots of energy to break. It's just bang, bang, bang. It's the same every time, year after year. And I've got so many of similar questions in the pack to show you how many times this comes up. I'm just going to get you to give him a nod because he looked like he was falling asleep. But you have to be able to describe the structure of diamond as well, and that might help you in a different sort of a question, which allows you to explain why diamond is hard. So diamond is hard because of its structure. Really, the difference between diamond and graphite is it's much more kind of three-dimensional structure. And again, I made little videos about all of these things in a bit of detail. But the key thing to point out here is, in this carbon that I'm pointing to, this one here, each carbon's making now 4 bonds per carbon. Structure and bonding, so we should say that it's covalent. You might want to just confirm what that means. Shared pairs of electrons between carbon atoms, and so the fact that means it's got a tetrahedral structure. I'll probably add also these are single bonds. And we should certainly say that it's a giant structure. So it's all the same stuff over and over and over again. So giant structure, giant covalent structure, tetrahedral structure. That just means that each carbon's making 4 bonds. That's the same mark really. And they're single bonds. And that means, by the way, in case you're ever asked this, that explains why diamond is so hard. It's the hardest natural substance that we know of. Okay. So again, absolutely slam dunk, you're going to get one of these questions. We're going to finish off with a bit on metals. I won't spend long on metals because for years, I look back at over the last couple of days, I looked back at every past paper and picked out all the questions from the triple papers. And just about every time it's either simple covalent, giant covalent, or giant ionic. But the last 2 years I've done a bit more on metals. 2 years ago, I think this question came from 2 years ago, which was explaining how metal conducts electricity. It was in your mock, so I don't want to spend time writing this out. But we talk about metals conducting electricity because they've got delocalized electrons, easy. And just like the graphite earlier on, they can flow through the structure, not throughout, but through. And they, what's the third mark? Shut it out. Carry the charge. Good. Right, so that's that one. Last year, I think it was, they did a question, if you've done the 24 paper, they did a question about why metals are good thermal conductors, and again, that's to do with the electrons being able to carry that heat energy around because they can move throughout the structure. Right, so quick fire questions before we go in a minute and a half. We've got a metal and non-metal. What is it? 3, 2, 1. Ionic, but I want you to say giant ionic, remember. Quick fire question. Which two substances, or two things here, have weak intermolecular forces between particles? What are they? Discuss. So, shout, cheer if I point to a right answer. You're not sure, are you? Right, so what about this one? We're all confident about water, but sodium chloride. Is sodium a metal or a non-metal? Is chlorine a metal or a non-metal? So it must be ionic. So that ain't it, is it? Not that one, that's ionic. Magnesium is a... So it ain't that one, that's metallic. Diamond is what? Giant covalent. Polymers though are what? Polymers, sit down. I'm going to let you go in 1 minute. Polymers are long chains, but what kind of interactions are between those long chains? It has to be right, doesn't it? Yeah. Okay. We stop there, shall we? There you go, that'll do. I'll send you this entire pack. You can have a look at them, look up the mark schemes if you want to later.